the main things to understand within electricity is static electricity and electrical circuits. And I guess the other thing that they want you to look at is electricity in, mains electricity. So, and that involved comparing alternating current with direct current, or AC and DC. If we look here underneath the subtopics, let's just get rid of that side panel. If we look at subtopics within this main topic of electricity, it will eventually, when it loads up, it's being really slow today. I don't know why my computer's struggling so much. Go to list view. We can see these are the subtopics within the topic of electricity, and it says whether or not they're GCSE, A levels, and so on. Now, resistivity is a topic that doesn't come up at GCSE, but it will come up at A level. So these are all the topics. But we're just going to give a general overview today, so we'll touch upon all these topics, or a lot of these topics. So what should we use to first introduce the concept? We're going to open up one of these circuit construction kits. Let's open up this one. You click on the link to open it up. And let's open up that there. Okay. Right. So we're going to play around with this. We're going to get a battery and some wires. You can have a go at playing around with this yourself, and by watching the video. They're all available on the resource database. Let's just get one light bulb for now, and we'll join this up. Can I pause this animation? It doesn't look like I can. Sometimes you can pause the animation, sometimes you can't. Usually you can on this, but never mind. Right. Yeah, this is the screen recording software that I've got lately. It's just, I think I might have to change it because it just seems to be really slows everything down. But anyway, so what is electricity then? If I close that, this light is going to light up. But why do you think lights light up when they are connected to a battery? Why do you think that happens? How do the electrons make it light up? Okay, well, what I'm going to do is I'm going to close this circuit up so we can see them moving around. They seem to be moving relatively slowly, but in reality, they've been moving quite a lot faster. And essentially, the reason why this metal here lights up is because the electrons are being forced through it and producing a sort of friction inside the circuit. So, and we can think about that as resistance. All right. So let's just get we haven't got Zoom, have we? I wonder if I can use this. So the first thing we're going so we know. Let's try that again. Resistance. Yeah, the screen recording software is terrible. It really slows everything down. I need to get a new one. So, okay, I'm just going to have to dictate this because the writing is basically unusable. Can't do it. So, frustrating, but never mind. I can't even close that. Great. So, the reason why this light bulb lights up is because the electrons are being forced through a thin bit of metal. This causes the metal to heat up. It heats up so much that it actually produces light. It produces in electromagnetic radiation. If we're linking it back to our previous topic, it's producing light waves or electromagnetic waves within the visible spectrum, and so it glows. That's how hot it is. Now, so we've got a couple of words we want to use here. The first one is current. So it says show current here. We're going to show the electrons moving around. So current is basically, we can think about it as the flow of electrons. but it's basically the flow of charge. Okay, if I had Zoom, I'd be able to write on here, but the other thing that I used just didn't work. So so a current is the rate of flow of charge. I'll use the whiteboard in a moment to summarize this. So current is the rate of flow of charge. In fact, I wonder if I can. Yeah, good. Okay, so first of all, we got current, and current is the rate of flow of charge. So it's how. That's the sort of textbook definition. Okay, so that's what they would say. Current is the rate of flow of charge. Now, what does that actually mean? It basically means how much charge flows by a point per second. Okay, and electrons actually carry charge. Electrons, we could say they have a charge, or they are charged. So we can call them charge carriers. Okay, so they are charge carriers. Okay, and so we can see here we've got these electrons moving around. They're carrying charge, and so charge is flowing. Right. So charge is flowing around. The amount of charge that is flowing around and how quickly it's flowing around, that is what the current is. Okay, so we can say that current can be defined as the total amount of charge that has flowed by a particular point divided by the time taken for that to flow. Okay, does that make sense? Okay, so that's what current is. So current is the rate of flow of charge. So we can work it out by the amount of the charge flowed divided by the time taken. The unit of current is amps, or can be written as A, and the unit for charge is coulomb, which can be written as capital C. I strongly recommend that you revise this yourself, but the video from this video, I just want you to get a general kind of feeling of it all. Okay, don't worry too much if you don't remember all this, and besides which, of course, you can rewatch it and look at the notes. But I would recommend having a go at it yourself, revising it yourself. So that's current. And the symbol for current is capital I, and the symbol for charge is capital Q, and the symbol for time is little t. So we can say that the current is equal to the charge over time. All right. So that's current. Let's make that heading bold, and we'll underline that. What's the next word that we need to? In fact, let's actually measure some of this, shall we? So we've got an ammeter here. In fact, let's look. What does advanced give us? Oh, add real light bulbs. What's that? No, we're not bothered with that. I'm going to disconnect this, and I'm going to connect up an ammeter, if it lets me. It's been really slow. Yeah. Okay. So apparently the current is 0.9 amps. All right. So that means every 1 second, 0.9 coulombs will flow through this ammeter. And the current is the same everywhere in this circuit. As you can see, these electrons are all moving the same speed all the way around. The reason for that is because electrons repel each other. So like charges repel, opposite charges attract. All electrons have a negative charge, so they're going to repel each other. They're going to try to get away from each other. So when one electron moves one direction, it'll push the one in front of it, and it'll allow the one behind it to move towards it as well. And that will be repelled from the one behind that, and so on. Okay. What does this one give us? Oh, okay. We'll have a look at that in a moment. The next thing to look at, let's turn it on now. The next thing to look at is voltage. Now, voltage is one that people often get confused with. So voltage is actually equal to, we can think about it, and I'm not going to put this the official definition yet. We can think about it as the energy per charge. Okay, so it's the energy per charge. If I have a load of electrons, which will essentially be a particular amount of charge, it will amount to a particular amount of charge, then we want to know how much energy do all those electrons have collectively. So if you have enough electrons that add up to 1 coulomb of charge, then we want to know how much energy do all those electrons have, and if they have 1 joule of energy, which is the unit of energy, then the voltage is 1 volt. So, in other words, voltage is going to be equal to, so voltage, which the unit for voltage is capital V, or volts, and that's equal to so it's energy per charge. Energy is measured in joules, capital J, divided by charge, which is capital Q, which we did earlier on. So I think what I'm going to do, actually, I'm going to just put before that another heading, charge. Okay, so what is charge then? I keep talking about charge. Well, the most important thing to understand about charge is that scientists don't really know. Scientists don't really know what it is. Yeah, we just know that some particles have it, some particles don't have it. We do know that charges repel and opposites attract, but apart from that, we don't really know what it is. And go on. Well, that is the same thing, yeah. So we know how we can use it. We know that in chemistry, ions have a charge because they have the amount of electrons is not equal to the amount of protons. So they could have a positive charge because they've got more protons, or a negative charge if they've got more electrons. And that's not a definition for charge. That's just describing. I mean, we know that you can count, or you can measure how much charge something has. So if we can say if the unit of charge is like the same, we say the unit of the charge of a proton, and then the charge of an electron is negative of that, and we can just say that's 1 unit or negative 1 unit. And so we can certainly measure how much charge an ion has. That's not defining what charge is, though. Charges, we can talk about how charge behaves, how things behave when they have a charge. It's still not really describing what charge is. But to be honest with you, there's a lot of the more you think about these kinds of things, especially within physics, the more you realize there are other things that we don't really know. We just sort of take it for granted. We think we know it until we actually have to start picking it apart, and we realize we don't really know it at all. Mass is another example. Scientists are still trying to fully understand what is mass and why does it do what it does. Sounds like we know it. Everybody is very comfortable with. So we know that mass is measured in kilograms. We know we're very familiar with kilogram. We know how to weigh things in kilogram. We know how to calculate the mass of something by measuring it, and so on. And we know that it connects with weight. We know how to use it, but we don't really actually know what it is the more we think about it. Anyway, that's a slight digression. Point is that if you get stuck up trying to understand what is charge, don't worry too much, because most people don't know what it is really. We just know that opposite things that have an opposite charge attract, positive or negative attract. Attract, and like charges repel, and obviously you can have a different amount of charge. I will say that let's give a figure here. Then charge of an electron in terms of coulombs is 1.66 times 10 to the power of minus 19. I don't know how to do powers on this. I wonder if you can do powers here. Don't know if you can do it or not. Anyway, that's hopefully you understand that means to the power of minus 19. So that's the charge of an electron. In fact, actually, it's minus that, and that's coulombs. That's how many coulombs it is. And then we got then just to so current was how quickly that charge flows around a circuit. Voltage is how much energy a certain amount of charge has. The symbol for voltage is V. Now, don't confuse. This is a classic. I mean, all within physics, units and symbols get confused all the time. But in electricity, it seems to happen a lot more. I'm going to put a symbol there. So the symbol is the character, the letter, or the letter that's used to that means the word. So Q is, we write Q instead of writing charge, but the unit is the thing that we measure it in. So when we say how much charge is there, we would say a number coulombs. Okay. Yeah. So maybe we could add a couple more details then. We could say measured in coulombs, and that's a capital C. Current is measured in amps, which is a capital A. So that's the unit. And voltage measured in volts, which is a capital V. Notice the potential for confusion here. Symbol for current is capital A. Sorry, the unit for current is capital A. The symbol is capital I. Let's write that there. But then same here. Unit symbol for charge is capital Q. Unit is capital C. But voltage, the symbol for voltage and the unit for voltage are both capital V. So that could cause some confusion. Oops, not that one. So voltage is equal to energy over charge. All right. What about resistance then? Well, I could certainly, if voltage is the amount of energy the charge has, then certainly if I increase the voltage, I'm going to increase the current, aren't I? If something has more energy, things are going to move more quickly, clearly. But this light bulb can be thought of as an obstacle. Essentially, it is an obstacle. The electrons are forced around. If I increase the size of this battery, I think I can. Yeah, let's increase the size of this battery. When I increase the size of this battery, you can see the current is also going up. Okay. So the light gets brighter as well, and the electrons move more quickly. So 43 volts now, and the current is 4.3 amps. So it's gone up quite a bit. But I can keep the voltage the same and still reduce the current. And the way I do that is by increasing the resistance. I increase the resistance, the current goes down, even for the same voltage. So the resistance, let's do a heading for resistance then. So the resistance is basically, which is capital R. It's basically how difficult is it for current to flow through. And basically, if something has a high resistance, then it's going to be difficult for the current to flow through it. If it has a low resistance, it's going to be easy for it to flow through it. So I've made it harder for the current to flow through this light bulb. In reality, how would I do that? Maybe I would make the bit of metal thinner, or maybe I'd make the bit of metal longer, so the obstacle is harder to get for the electrons to get through. Now, it relates current to voltage in this way. Resistance is equal to voltage. Let's use the symbols again. Is equal to volt. Actually, let me just be consistent. I've been using units in the brackets there. So, okay, I can't. I wonder if I can get a symbol for omega. It is, yeah. It's like a horseshoe type thing. It's a Greek letter. Okay, let's omega. I do this all the time. I search omega, and it gives me a load of watches. Omega symbol. And then just, copy, Okay. Back to here. So the let's actually measure it. Let's do here as well. So measured in ohms, and the symbol for that is an omega symbol. Omega. And we can calculate it by doing voltage over current. So to use the symbols, it's going to be R is equal to V over I. Now, do not confuse what I've just written there with something called Ohm's law. This is not Ohm's law, and we may have time to briefly touch upon Ohm's law. It is just how to calculate resistance from current and voltage. Okay. So there is something called Ohm's law, and often this formula gets confused. People say that's Ohm's law. It's not Ohm's law. It's just a way to calculate resistance. I haven't explained to you what Ohm's law is yet, but we've touched upon the four main words that are going to be used in electricity. It's usually these three here, but I've started to explain this one as clearly as we can, because it comes up in the other one, in these two here. So what is Ohm's law then? Well, Ohm's law, so let's do Ohm's law. Probably going to be related to resistance, isn't it? Because resistance is measured in ohms, and so what is Ohm's law? Ohm's law is, so you can say if a component, and when I say component, I mean a light bulb, anything that goes in a circuit, light bulb, a buzzer, a resistor, whatever it might be. If a component follows Ohm's law, then the resistance stays constant at constant temperature. So if the room is kept constant, if the temperature of the room or the temperature of the experiment is kept constant, the resistance of the thing will be kept constant too. So the resistance stays constant and I should say maybe at different voltages. Let's just move this up. Yes, that's exactly what it means. Yes, yeah. So now, if we plotted this on a graph, and we'd probably want to do a bit more of this next time, if we plotted this on a graph, if we plotted voltage against current on a graph, you would get a straight line, because if you think about it, the gradient is going to be y over x, and either voltage is going to be v against I or I against v. So the gradient will always be constant because the resistance is constant. So we could say that. So therefore, voltage is directly proportional to current for these components. If I were to double the voltage, then that would mean the current would double. Okay, that's what directly proportional. And it's worth maybe putting a bracket around directly, because somebody recently lost a mark in a test when she wasn't sure what kind of proportion it was, and so she just wrote proportional. Proportional means directly proportional. And then you can have also inversely proportional, which we won't go into at this moment. I wanted to just make a point here that this point, when I said earlier on that this gets confused, we can say that for sure that voltage is equal to I'm just going to rearrange this equation up here now. Voltage is equal to IR, and if the resistance is constant, then we would see that voltage is equal to I multiplied by some constant. And so we can see, therefore, that the resistance is constant. This is not the case for all things. So it's not a law like a universal law. It's just that some things follow Ohm's law, some things don't. Okay, so this light bulb actually does not follow Ohm's law. A resistor does, and a regular wire does, but this light bulb does not. Neither does an LDR. Oh, does an LDR follow? I'm not sure. Probably not. Thermistor doesn't. A diode doesn't, which some of these things we'll look at in a bit more detail next lesson. But whether something follows Ohm's law or not, you can still use this equation here to calculate resistance. So it is not Ohm's law. It is just a way of calculating resistance. If you know the voltage and you know the current, you can calculate resistance using that. Okay?